we're recorded. So if you don't want your face showing up, turn off the camera. Similar thing, keep your microphone turned off unless you want to ask a question, and Linda is happy to have them during the seminar. Captions will, I believe, appear. In other words, live transcript, you can turn that off with the live transcript button at the bottom of the, at least on my computer, at the bottom of the Zoom panel. Although it may be interesting to see what it does to Linda's New Jersey accent. Okay, so it's my privilege to introduce Linda Cummings, who's a professor in the Mathematical Sciences Department at the New Jersey Institute of Technology, and has been a loyal supporter of the Newton Institute down the years. Her title is in front of you, so I won't read it out, but we'll hand straight over to you. Thank you, Linda.
Thank you, John. Hello, everyone. Thanks for joining for the talk. And thanks, of course, to the organizers for putting together such a great program, especially under the trying circumstances, and also for the invitation to speak today. So I'll be telling you about aspects of some work that John King and I did quite a long time ago when I was at the University of Nottingham on selection problems in Hele-Shaw free boundary flows. And although it's work, although it's such old work, I've never actually given a talk on it. So this is my first time speaking about this work. So a bit of background, the Hele-Shaw cell is named after Henry Selby Hele-Shaw, shown here in his motor car in about 1902. So he was a mechanical and aeronautical engineer and inventor, best known perhaps for inventing the variable pitch propeller, as well as the Hele-Shaw cell, of course. So the Hele-Shaw cell consists of two parallel glass or perspex plates that are separated by a narrow gap. And the gap is wholly or partially filled with viscous fluid. So in Hele-Shaw's original paper, which appeared in Nature in 1898, he actually used the cell to visualize two-dimensional streamlines around various solid obstacles within the cell, as you can see in this lovely image of streamlines around a flat plate here. But since that original 1898 paper, the cell has become much better known for the free boundary problems that it leads to. So when the cell is only partially filled with viscous fluid, there's a free boundary between, well, we'll be thinking about air and a viscous fluid in the cell. So there's a free boundary between the air and the liquid, and you can make that move if you apply pressure gradients. So if you suck or inject viscous fluid or indeed air into the cell. And so that will lead to a moving boundary problem. And if you assume that the air behaves passively, so it's just a constant pressure fluid, which is reasonable under most circumstances, then that leads to what's known as the one-phase problem, where you just have to solve the governing fluid dynamics equations within the viscous fluid region, subject to appropriate boundary conditions at the moving boundary. And that's what's going to determine the free boundary evolution in time. So what are the governing equations? Well, it's easy to show that the pressure in the viscous fluid region is independent of the coordinate z that's perpendicular to the cell. So it's a function only of in-plane variables x and y, and of course time t, which is largely suppressed throughout this talk, but everything is time dependent because the boundary is moving. So the flow is two-dimensional. It's purely in the xy plane, and the Navier-Stokes equations reduced to the form that's shown here, these two equations in the x and y directions. Excuse me. So everything here, I should say, is in dimensionless form. So we've non-dimensionalized lengths and time and everything. So to keep things simple. So you have to solve this dimensionless form of Navier-Stokes equations with no slip and no penetration conditions on the two plates of the cell. And obviously that gives you a velocity profile that's parabolic across the cell. And what you then do is you average your velocity components across the depth of the cell. And when you do that, you easily find that the pressure in the fluid satisfies the two-dimensional Laplace equation and also acts as a velocity potential for the depth averaged velocity field. So even though the flow is completely dominated by viscous effects, these equations here that you see are the Stokes equations for fluid dynamics. So even though it's completely dominated by those viscous effects, the equations that come out are actually the same as for two-dimensional inviscid flow, which is why those streamlines in Hele-Shaw's original paper faithfully reproduced those for inviscid flows around two-dimensional obstacles. And that was actually a key goal of his original paper, was to come up with a way for visualizing such streamlines. But as I said, we're interested in the moving boundary problem. So if you're thinking about moving boundary problems, then you need to solve the Laplace equation for the pressure in a time-dependent domain that has a moving boundary. So you have to solve that equation subject to boundary conditions on the free boundary, which I'll be denoting by the omega of t. So you need boundary conditions on the boundary. You also need an initial condition because the domain is moving. So you need to specify the initial fluid domain omega 0. And you also have to specify any driving singularities in the pressure. And that includes far field driving singularities, such as a pressure gradient, for example, in the far field. So the boundary conditions that are typically applied for the Hele-Shaw problem are the dynamic boundary condition, which balances the jump in pressure across the interface by surface tension times curvature. And in almost all of the literature, the curvature here is taken to be the two-dimensional curvature of the two-dimensional curve that defines the interface. Excuse me. And if you assume that the pressure is identically 0 in the air region, we've already said that the air region is just passive, so you may as well assume the pressure was identically 0 there, then that gives the dynamic boundary condition in the form shown here. So pressure equals surface tension times curvature at the moving interface. Now, in many applications, you can show, or you can assume at least, that this dimensionless parameter gamma that characterizes the surface tension, you can assume that it's small, and it's common to set it to 0 in the theory, and that gives the widely studied 0 surface tension problem, where in fact you just say the pressure vanishes on the moving boundary. So that's one boundary condition, dynamic boundary condition. Because the boundary is moving, we also need an additional kinematic boundary condition that tells you how it moves. And this condition comes from the observation that the normal velocity, which we denote by v sub n of the boundary curve, has to be the same as the normal velocity of fluid particles at that boundary. So this expression v dot n, which of course we can express using the pressure. So the kinematic boundary condition is dp by dn equals minus vn. And the resulting model certainly has widespread physical relevance. So it's received a lot of attention from many different communities over the years. So, it can be used to represent free surface flow through a porous medium. So flow of groundwater, for example, Darcy flow, problems in oil recovery, the one-phase Stefan problem for melting and solidification if you take the limit as the specific heat goes to 0. There's problems in electrochemical machining and forming. Problems with squeeze films is closely related to, but it also has a large number of mathematical features that make it interesting, particularly in the case of 0 surface tension. So for example, for that problem, you can show that there's an infinite set of conserved quantities or moments. That problem has deep connections to the theory of integrable systems, random matrices, and so on. So a lot of the research interest in this problem does stem from the mathematical community. Stability of solutions is obviously important, particularly if you're thinking about applications such as oil recovery. So the free boundary is well known to be unstable when the viscous fluid is retreating. So if air is displacing a viscous fluid, that's an unstable situation, whether or not the surface tension is set to 0. And some very well-known examples of this instability are the Sefman-Taylor finger, which you see here on the left. So here we're injecting air from the left of the cell. So this is an air finger that you see here. And here's the radial analog of that same problem. This is a paper due to Patterson in the Journal of Fluid Mechanics in 1981. So here an air bubble is being injected through this syringe. You can see that initially the interface is approximately circular, but then it destabilizes and forms these lovely fingering patterns. So this is a time-lapse photograph that's being shown here. And there's been a lot of nice subsequent work on these problems, far too much to mention here. But I should at least say a little bit about the Sefman-Taylor problem, even though that's not really the subject of this talk. But the Sefman-Taylor problem is especially well studied because of this puzzling selection issue. So within the 0 surface tension approximation, so that's setting that parameter gamma to 0, it's been known for a long time that the Safman-Taylor problem has an infinite family of finger-shaped solutions in which the finger width lambda as a fraction of the channel width is arbitrary. Now, however, as you let the surface tension parameter gamma go to 0 from above, so the non-zero surface tension problem, what you find is that a single member of that solution family, the one with lambda equals 1/2, the finger occupies 1/2 of the channel width, is selected. And you see this both numerically and experimentally. Now, the problem of how this selection occurs mathematically took nearly 30 years to resolve, despite lots of very clever people working on it. And it relies on asymptotics beyond all orders. And here I'm showing you just a few of the key names who worked on this problem. This is just a list that I threw together quickly from memory, so I'm almost certainly missing some important names off. Apologies for any omissions. So what are the main challenges in this zero surface tension Hele-Shaw problem, or in the limit as you let surface tension go to 0, for example? Well, first, if you look at the unstable situation, so the case where air is displacing a viscous fluid, well, one issue that arises is that the problem with the zero surface tension problem, with when you set gamma to 0, that's ill-posed. So perturbations there will grow without bound as the wave number of the perturbation goes to infinity. So shorter and shorter wavelength perturbations grow arbitrarily quickly. Now, if you take the surface tension parameter to be positive, well, that will regularize the problem, so it won't be ill-posed anymore. But then the problem is that the limit in which that parameter gamma goes to 0 is singular. So regular perturbation techniques fail when it comes to analyzing the Safman-Taylor finger selection problem, for example. And it turns out that terms that are transcendentally small in the surface tension parameter gamma are those that govern the selection. So with that preamble, let's now consider the problem that I'll be talking about today. So I'll be thinking about Hele-Shaw flow. This is the experiment that actually leads to the problem I'm going to talk about. So if you take a Hele-Shaw cell with a finite blob of viscous fluid within it, so here's the experimental setup, here's the viscous fluid, air outside here, then this is the moving boundary problem that the pressure in that cell satisfies. So we have the Laplace's equation in the fluid domain. We have P equals surface tension times curvature on the interface. And we may or may not want to set that surface tension parameter gamma to 0. We have the dynamic boundary condition on the moving interface. And we want to think about the case where fluid is, injected or removed at the origin, although removal of fluid will be the unstable situation. So I'm going to take Q to be the parameter that represents the strength of the source or sink in the problem. And so if you want to model that, then you have to specify the right form of the pressure singularity at the origin. So it turns out the pressure has a logarithmic singularity there. So this is what the local behavior of the pressure looks like as polar coordinate r goes to 0. And of course, as usual, we have to specify the initial fluid domain omega. So, excuse me, I just need to drink a bit of water. So if there's so if we didn't specify that pressure singularity, nothing would happen, obviously. So you certainly need a singularity in the pressure to drive the flow. If there was no singularity, the pressure would be 0 everywhere, the boundary wouldn't move. So this is what's driving the fluid. Now, to think about what happens to solutions, particularly in the unstable case here, it's useful to note that if you set the surface tension parameter gamma to be 0, then you can easily show that that problem is time reversible. So if you inject fluid, that's the case Q greater than 0, into an initial domain, omega of 0, for a certain time, call it tau, to obtain the domain omega tau, then this free boundary evolution with the injection would be exactly reversed if you started with the domain omega tau and ran time backwards through tau units. But equivalently, if you start with a domain omega tau and runtime forwards through tau units with the parameter q less than 0, so that's the case of a sink at the origin, you're again going to obtain the fluid domain omega 0. So basically, P goes to minus P in the solution when we reverse time or when we change the sign of Q. So you've got this time reversibility in the zero surface tension problem. Okay. Now, an important consequence of this is that that makes it easy to show that solution breakdown is almost inevitable in the zero surface tension problem with suction. So to think about this, if you start by injecting fluid into a single point source at the origin, that leads to an expanding circular fluid domain. That's the unique solution. Okay. So if you reverse this evolution by changing the source to a sink, then you're going to remove all the fluid through the point sink. But because solutions to this problem are unique, that means that the circle with the sink situated at its center, that's the only way that you can remove all fluid through the sink. And if you start with any other initial domain or any other placement of the sink, even if you start with an initially circular domain, that must lead to breakdown of the solution before all fluid is removed. So that would happen either by self-intersection of the boundary, in which case you've got a change in connectivity of your solution domain, and that would change the nature of your problem. You'd have to go back to your underlying assumptions, reformulate and start again. So we're not considering situations like that in this talk. But if connectivity doesn't change, then what has to happen is that the solution breaks down by formation of a singularity in the free boundary. And I'll say generically, that is to say that for almost all initial conditions, that breakdown would occur via a 3/2 power cusp in the zero surface tension problem. Okay. So if you allow non-zero surface tension and set a parameter gamma to be a positive number, then you should avoid that cusp formation. But how does that happen? Well, to see that, it helps to look at numerics. So around 20 years ago, a number of groups carried out careful numerical simulations of Hele-Shaw flow with a point sink at the origin, where the initial domain, so you're not seeing all of the evolution here, but the initial fluid domain here was a circle, and the sink was situated somewhere off center. So this line here is not a diameter of the initial circular domain. Okay, so we know that the zero surface, so this is a problem that you can actually solve exactly when the surface tension parameter is set to 0. And what you find for the zero surface tension problem is that the free boundary would break down via formation of a cusp just at the point where I'm holding my mouse here. So you'd have this kind of apple type shape. Okay. Now, obviously, when you set surface tension to be some small positive number, you don't see that 3/2 power cusp forming. What you see instead is that, well, here on the right, it's useful to look at this zoomed image of this region of the domain on the left. So you can see that the free boundary starts to get pretty close to that cusp configuration. That's this first curve shown here. But then something quite different happens. The free boundary, the problem completely changes its mind about what it was going to do and turns around and starts to form this spindle type shape. And ultimately, I mean, simulations were halted at this final time here, but ultimately it looks like the solution is going to break down by this wedge type shape of air entering the origin here, which is the location of the point sink. Okay, so the free boundary starts to form a cusp, then radically changes its mind, approaches the sink as this spindle shape, or ultimately a little wedge, if you look very at the very tip there. And as an aside, although again, we're not really talking about Sefman-Taylor here, but related behavior was found for the Sefman-Taylor problem by Siegel, Tanvir, and Dye. So they carried out numerics for small positive surface tension. And what they did was they started with initial data that corresponded to a lambda equals 1/3 zero surface tension finger solution. So here, the dashed curves that you see here, those are the zero surface tension solution, which forms a regular Sefman-Taylor finger of width 1/3. Remember, any finger width is allowable when surface tension is 0. but the solid curves show simulations at small positive surface tension. These curves, these figures A and B are just showing two different values of the surface tension, but they're both very small. But again, you see similar behavior to what was seen in those numerics on the previous slide, where the positive surface tension solution starts out by following the zero surface tension behavior, but then it changes its mind at this point here, and it remembers that it's supposed to form a lambda equals 1/2 finger. So you get this deviation from the zero surface tension initial data that you started with, and it starts to form the finger of width 1/2 instead. And so here's showing the phi boundary evolution. What you see in this figure over here is showing the measured finger width as a function of time in those simulations. So again, you can see that this is the zero surface tension solution where the finger of width 1/3 is allowable. And these are showing a series of simulations for increasingly small, well, decreasing values of surface tension, I should say, where you see this marked deviation from the initial data occurring. And so Siegel, Tanvir, and Dye studied this behavior in quite some detail, and they came up with a theory of so-called daughter singularities, which explains this evolution here, where the solution starts to rapidly diverge from whatever it wanted to do initially. So to go back to the problem that we're looking at, there are a number of questions that are raised by this type of behavior. So first question, of course, is what's behind this behavior? And I don't really want to talk about what's going on here, that initial divergence from the exact zero surface tension solution. That is something that Saleh Tanvir could tell you much more about with his theory of daughter singularities. But for this talk, what I'm going to think about is what's happening down here when the solution finally breaks down. So it looks like the phi boundary is going to enter the sink in the form of a wedge. So, you know, why a wedge? What governs the final angle of that wedge as the phi boundary approaches the sink? And is there a zero surface tension, what you might call a paradigm solution, that can be usefully considered to think about problems of this kind? Now, obviously, we don't want to think about the original zero surface tension problem that was posed, where we start with a circle with an off-center sink, because the behavior has dramatically deviated from that solution. It's forgotten all about that initial state. So the right zero surface tension problem to think about to explain this final time behavior has to be something else. So, so what's the right problem to think about? Well, based on the numerical observations, the speculation is that the correct zero surface tension limit to think about, if you want to think about, you know, how the phi boundary generically breaks down in problems of this kind, then you should really be thinking about the phi boundary entering the sink locally as an air wedge within finite time. How would we construct such solutions? How do you come up with a zero surface tension solution and guarantee that it enters the phi boundary as enters the sink as a wedge? Well, that's where thinking about the time reversibility of the zero surface tension solution comes in. So what we need to do is take an initial fluid domain omega at time 0 to be an unbounded domain with a single infinite air wedge. So that's the red domain that's sketched here. That would be the initial domain. It's got air here, fluid where the color is. And drive that evolution by injecting fluid at the origin in the cell. And what's going to happen is the phi boundary will move off, as indicated by the blue curve in the blue fluid region, and instantly smooth, basically. So, you know, but appealing to the time reversibility, if I were to start with this blue curve here, and instead of injecting fluid, suck fluid out of it, then we're going to get the solution family that we want. The phi boundary will enter the sink as a wedge locally. Okay. So, and we can actually consider a slightly more general version of this problem. So, you know, in those numerics that I showed you, there was just a single wedge entering the fluid at the breakdown time, sorry, entering the sink at the breakdown time. So, mathematically, we can be slightly more general. So we can construct solutions in which breakdown is achieved via an arbitrary number, let's call it capital N, of such air wedges that reach the origin simultaneously and symmetrically. So here is just a sketch showing the setup when 4 such wedges would reach the origin simultaneously. We've got air here, fluid here. There'd be basically 4-fold symmetry about the origin. And, the question is, what happens to this free boundary over time? Can we construct this family of solutions? And of course we can. So the solution method that we use to construct these solutions uses complex analysis. So instead of being the coordinate perpendicular to the cell now, z is going to be x plus iy, the complex planar coordinate. So here's the moving boundary problem that the pressure satisfies. And when we think of constructing our solution family, this parameter, surface tension parameter gamma, will be set to 0. We have Laplace's equation, dynamic boundary condition, kinematic boundary condition, driving pressure singularity, given initial domain. And now remember, we're thinking about constructing the solutions by having a point source at the origin. And so the initial domain that we specify is going to be a wedge. So because the pressure is harmonic, you can write it in terms of a complex potential, which we call W. It's a function of Z and T in general, so the pressure will be the real part of this complex potential. And you know that this complex potential has to be analytic in the fluid domain, except at the origin, where it's going to have the right singularity to match the pressure driving singularity. So W also has to have a logarithmic singularity near the origin. Now, you know that the moving boundary is going to be an analytic curve, except for our solution family, the only exception to that will be at time 0 and at the origin, where at the initial instant, the free boundary is non-analytic at the source or sink. But other than that, the moving boundary is going to be an analytic curve, and you can describe it in terms of an object known as the Schwartz function. So it's a complex analytic function, at least in some neighborhood of the boundary. Since the boundary is moving, we have to allow this Schwartz function g to be a function of the complex variable z and time t. And the Schwartz function is, it's the unique unique function, complex analytic in some neighborhood of the boundary, in terms of which the free boundary can be described as the set of points for which the complex conjugate of z is equal to g of z and t. Okay, that's how the Schwartz function is defined. And some of you may be familiar with it, some of you may not, but it's just one way to represent the free boundary. But what's convenient is that the Schwartz function is guaranteed, as long as your boundary curve is an analytic curve, then the Schwartz function is guaranteed to be complex analytic in some neighborhood of that curve. Now, how does that help us? Well, you can show that there's a deep relation between the complex potential W and the Schwartz function of the boundary curve. So if you manipulate the boundary conditions, the kinematic boundary condition and the dynamic boundary condition, then you can show that on the boundary, they're related as follows. So we have dw by dz equals 1/2 dg by dt plus this rather messy looking term here, which is the term that contains the surface tension parameter. And that comes from manipulation of the boundary conditions. So in the first instance, you can just say that this relation holds on the free boundary. But then you can take that further because you know that the complex potential W is complex analytic on the whole fluid domain, except at the driving singularity. And you know that the Schwartz function G is guaranteed to be complex analytic, at least in a neighborhood of the boundary curve. Well, what that means is that this identity here can be analytically continued away from the boundary curve. And you can say that it holds wherever both sides are defined. But in particular, it holds on the fluid domain omega. Okay. Now, for the zero surface tension problem, which we're focusing on for the moment, then this equation here forms the basis of a remarkably simple solution method, really. I mean, there's technicalities to how you apply it, but the concept is very simple. So loosely speaking, if you can find a Schwartz function, g of z and t, And I should mention, I mean, many of you may know this, but not any old complex analytic function is a Schwartz function. It has to satisfy certain consistency conditions. So this part is not quite as simple as it sounds here. But if you can find a Schwartz function, g of z and t, that is complex analytic on the fluid domain, except at the origin, where it has the right singularity that matches the singular behavior that you know the complex potential has, then it must represent a possible solution to the Hele-Shaw zero surface tension free boundary problem. Okay. I guess I said some of this. Schwartz functions are non-trivial to express explicitly. I said that not any function is a Schwartz function. And not only that, if you have an analytic function that you can, that you have some regular representation for, it may be non-trivial to write on the Schwartz function for that. So, so the way you accomplish this in practice is you can access the Schwartz function by means of an intermediate conformal mapping from some fixed canonical domain onto the moving domain that you're looking at. That enables you to essentially to represent the Schwartz function parametrically in terms of an intermediate complex variable in the mapping plane. But these are all just technicalities that I don't want to get too deeply into in this talk. So by introducing such an intermediate conformal map, we can access an infinite set of solutions that are valid for zero surface tension, and they're parameterized by the number of wedges n that form and the wedge angle beta. So, and this shouldn't be too surprising because, we're solving the initial value problem with the wedges. So it's fairly self-evident that I can choose how many wedges I want and I can choose that angle, okay? So, and then when we reverse time in those solutions, we can construct any solution in which the free boundary enters the point sink within finite time in terms of any number of wedges that you choose. Here I'm showing you 1, 2, and 3 wedges, and any wedge angle that you like to specify, okay? And these are similarity solutions, I should mention, at least in the zero surface tension limit. So the similarity variable is z over root t. So similar to the Sussman-Taylor problem, there's a selection challenge here. Which of these solutions are going to be observed in the limit that the surface tension parameter goes to 0? So, so to think about that, let's go back to our Schwartz function equation. So our family of zero surface tension solutions obviously has a Schwartz function G that is analytic on the fluid domain omega, except at the origin. Okay, so this term is not present in zero surface tension. So we're just looking at this simple governing equation here. So the Schwartz function has to be analytic, except at that driving singularity of the complex potential. But you can see what the problem is going to be, that those zero surface tension problems in general are going to have zeros in the derivative of the Schwartz function. Now, that's fine when gamma is 0, but it's certainly not fine whenever the surface tension is non-zero. Okay, so I can have zeros in dg by dz when gamma equals 0. When gamma is non-zero, that's not so good. So, and it turns out that all members of the solution family that we write down have zeros in the derivative of the Schwartz function. Okay, and of course that's a problem because when gamma is positive, there's nothing to balance those. So when we look at our solution family on this infinite family parameterized by the number of wedges and the wedge angle, we find that the roots of the zeros of dg by dz either occur as two complex conjugates in the complex plane, or exceptionally, there's one repeated root at some specific wedge angle for which those roots, coalesce in the complex plane. So you get a repeated root. So since our solutions are all similarity solutions, this rather complicated partial differential equation here can be simplified a little bit. So you only have to think about an ordinary differential equation if you switch to similarity variables. So, we want to think about what happens to this equation when gamma starts to be, when gamma is non-zero. Okay, so to do that, we switch to similarity variables. which we know because we have the zero surface tension solution. The only slight problem with doing that is that you can only strictly write this equation in similarity variables if you are prepared to allow the redefined surface tension to depend on time. We're not too worried about that because we're interested in the limit as surface tension goes to zero. So having it time dependent is not too much of a problem. So in similarity variables, then we're interested in roots of the derivative of the Schwartz function and what goes on in the neighborhood of those roots. So what happens locally? Well, let's first of all just think in terms of schematics. So here's the Schwartz function governing equation in similarity variables. And here I've written it in terms of h, which is the derivative of the Schwartz function. So we're interested in what happens near a zero of this function h of z in similarity variables. So if you think about a zero of that function, call it z star, then for the local picture, there's two possibilities based on what we said on the previous slide. We either have, and here I'm looking locally at the absolute value of this function h or g primed. So we either have a simple zero, in which case the local picture in the zero surface tension case has to look like this, or we have a repeated zero, in which case the local picture has to have a bowl shape locally in the complex plane. So I'll refer to these two cases as case one and case two, simple zero, repeated zero. And then the idea is what happens locally to this picture as we let this parameter gamma hat become positive. We have to regularize the thing locally. So one assumes that in the case of small positive surface tension, case one would have to look something like this, case two would have to look something like this, just pictorially. Excuse me. So near the zero, we can construct naive local expansions in each of these two cases. So you can, we're looking in the neighborhood of a zero. So we can redefine a coordinate z tilde, which is zero at the zero of the derivative of the Schwartz function. And we can also redefine a local coordinate, which I'll call big Z, in terms of some characteristic inner size. That's this parameter delta here. And delta's got to be different in the two cases in general because the scalings are different for a simple zero and a repeated zero. So in the case one, simple zero, the what you'd call the outer behavior in the coordinate z tilde has to be linear in z tilde as z tilde goes to zero. And for the case of the repeated zero, local behavior has to be quadratic as z tilde goes to zero. So you can also infer by going back to the governing equation for the Schwartz function, you can infer what the inner scalings have to be in the two cases. So the rescaled version of this function h, which is the derivative of the Schwartz function, and a rescaled complex potential. So I'm using uppercase letters to denote everything in the inner region. And you can also, when you look at that inner form of the equation, you can also infer the characteristic size of the inner regions in both these cases. So in case one, the inner region is of size surface tension to the 2/7. Case two, it's surface tension to the 1/5. And so in both cases, you can write down outer and inner equations. Okay, so the outer equation in both cases is this ordinary differential equation here. The inner equation in both cases is the ordinary differential equation here, but delta is defined differently in terms of gamma hat in those two cases. Okay. So, so we have, outer equation, inner equation, and you can, you can sort of turn the handle. You can construct inner and outer expansions in each of these two cases. So in case one, you find that the inner and outer expansions have to take the form represented here. In case two, they have to take the form represented here. I don't expect you to absorb all these details, but this is when you turn the handle, this is what you find the local behavior would have to look like. And as you might expect, for those of you who are involved in this program, as you might expect, there's no obvious roadblocks when you take this kind of naive approach, constructing inner and outer expansions, applying the matching principle, and so on. So although you can say that case 2 looks a lot nicer than case 1 in the sense that there's no branch points and things to deal with, there's no obvious way to exclude a case 1 scenario. So nonetheless, it's our conjecture that case 2 is the scenario that's selected in the limits that gamma goes to 0 from above. So that is to say, the selected solution from that infinite solution of 0 surface tension, from that infinite family of 0 surface tension solutions, the selected one is going to be the one that has the repeated derivative of the repeated 0 of the derivative of the Schwartz function. But of course, this is something that's going to take asymptotics beyond all orders to prove rigorously. We haven't done this yet, or at least I haven't. Maybe John has without telling me. I haven't done this yet. I can show you a comparison with what our 0 surface tension solution family looks like when you compare it with the small surface tension numerics of Sinistros, Hu, and C. So what you're seeing here is its tangent angle to the free boundary plotted as a function of arc length or scaled arc length along the boundary. So we took our solution and we plotted it on the same scales as the numerics of Sinistros, Hu, and C. Obviously, once you move away, so here, of course, is the point that represents the sink, the point source or sink. This behavior out here, of course, is because they started with an initially circular domain and they're showing us the tangent angle for the whole free boundary here. But when you focus in on the local behavior, which is how the solution is breaking down and how we believe all small surface tension solutions with a single point sink have to break down in this way, then we see a very good agreement in that local behavior. To sort of make a further comparison, so for each value of n, so I said that we can construct any number of air wedges going into the sink in finite time, and here's n equals 1, 2, and 3. So for each value of n, you can calculate the fraction. We can define the fraction of kind of its unit sector that the selected air wedge occupies, and you can plot that. And here I don't know why this is negative actually, but yeah, sorry, I'm blanking on what this horizontal axis here is, but what I'm showing you on this figure is as the number of wedges that go into the origin goes to infinity, we approach the Sefman-Taylor limit, okay? Because you can think if you increase the number of wedges that are going to enter the origin, then within its characteristic sector angle, 2 pi by n, each of those is going to start looking like a Sefman-Taylor finger as that parameter n goes to infinity. And so we would expect our solutions in that limit to pick out the lambda equals 1/2 limit, and indeed that's the case. So I don't really want to say much more than that today because, this is meant to be a speculative talk. As I say, it's a problem that I have not resolved yet. But just to sort of summarize what I think are the key points here. So the dynamics of the Hele-Shaw free boundary problem are governed by this partial differential equation for the Schwartz function of the free boundary. So the derivative of the complex potential is related to the Schwartz function of the free boundary, not only on the free boundary, but everywhere in the fluid domain. And this equation simplifies when you have a family of similarity solutions, so it's somewhat simpler to study. So when you look at this governing equation, it's clear that zeros of the derivative of the Schwartz function are fine when surface tension is 0, but they are certainly not fine whenever surface tension is positive. And so we believe that the question of which solution is selected from a family of 0 surface tension solutions in the limit as surface tension goes to 0 from above is going to rely on a careful analysis of how these zeros of dg by dz can be regularized. And our unproven conjecture is that it's the solution with the repeated 0 in dg by dz that is selected in that limit, and that this should be a fairly general result, because this partial differential equation holds not only for the problem that I showed you, but it holds much more generally for all Hele-Shaw free boundary problems. And why is the solution family that we studied here of interest? Well, we anticipate that this solution family represents generic local solution breakdown for not only for the initially circular domain that the numerical people looked at, but basically for any finite fluid domain that's driven by a single point sink. Locally, the free boundary has to break down somehow, and we believe that this breakdown by wedge entering the sink locally is going to be generic, regardless of what initial condition you start from. So with that, I will stop, and I'd just like to acknowledge my PhD advisors from way back when, Sam Harrison and John King, who got me interested in Hele-Shaw problems in the first place. And of course, sorry, did I say Sam Harrison, John Ockenden, and of course, John King, with whom I worked on this problem. So thank you.
Thank you, Linda. That was grand. Questions for Linda?
And I can refer them to you, John, since
that relies on.
Can I ask a question?
Phil.
Phil, yeah.
What's your intuition of why the double root case is selected?
Other than being mathematically a lot nicer. I mean, you mean mathematically or physically?
Well, I think the way that you pitched it, it's not physical, right? So it's not a stability analysis. You're not saying that if I add time dependence into this, that case 2 is selected. I think what you pitched it as was, if I take the limit of gamma tending to 0, that the solutions, if I understood it correctly, you're saying the solutions for case 1 are invalid? No, I'm not sure.
Well, I mean, I suspect they're invalid, but I haven't shown that they're invalid. So, obviously, these are what the, when you do a naive inner and outer expansion, this is what you find the asymptotic expansions have to look like in the inner region and the outer region. In case 1, where the 0 is simple, and case 2, where the 0 is repeated. And, you can see that in case 1, you're going to have branch points and everything to deal with. In case 2, things look much more straightforward. But, that's not a proof. It's just saying that things look much more straightforward in the case 2 scenario than in the case 1 scenario.
And it's
I should say this is a problem that I haven't thought deeply about in a long time. So, but it is one that I thought this audience might have some insight into. And
I mean, the zero surface tension problem of you can have these multiple configurations. I mean, you've shown here you can have these multiple configurations where you have different angles, right? You're approaching different angles and coalescence of roots, and it's just not. Yeah. It's not obvious that from the mathematical perspective, it's not obvious to me that you shouldn't have things with branch points.
Yeah, no, I agree. It's
not as nice.
I agree. And that's, but so I don't have a good mathematical answer for you. They're clearly mathematically distinct, the two cases. And there's no hope of getting some kind of numerical check Well, it depends what you mean. I mean, numerically, we believe that the angle that we find for the repeated zero solution does agree with what they find numerically. So we're relatively confident that, well, at least I'm relatively confident that this is what's being selected, that it is selecting the repeated root. But I don't have any kind of strong argument at the moment, other than the fact that it's a clearly distinct case. This is one member of the solution family that is clearly distinguished from the others. Mathematically, it has different behavior local to the problematic point.
Thank you.
And it's probably easiest to, it will certainly be easier to study the ordinary differential equation version of this. So, looking for zeros of H in this equation here, which is just an ordinary differential equation.
This may or may not be relevant, Phil, but one of the differences from Saffman Taylor is you're not trying to find an exact solution to the problem. You're only finding an asymptotic solution. You can make gamma, if you choose a particular time dependence for gamma, you can make the problem with surface tension in it have similarity solutions, which would give you the closest analog to Saffman Taylor, but we never.
Yeah, the choice of gamma being gamma of t under the similarity scaling is really weird, because you said you compare it to physical experiments, but in physical experiments, presumably you're fixing your gamma.
Yeah, I mean, definitely. And yeah, no, I agree. In a physical experiment, it is definitely for fixed gamma, but I'm comparing the physical solutions with, with our solution for which gamma is 0.
But it means that if you do a physical experiment, so the thing is you're taking the limit that gamma tilde, which is your new gamma tending to 0. It means you're crossing all these, you're kind of taking the limit of the fixed gamma problem in a very peculiar way. You're like moving across different branches in your bifurcation space. And I had wondered what the hell that means, but it was, yeah, I don't know. I've not seen that before. I've not seen that gamma as a function of t before.
Any other questions? Because if not, we'll do the usual thing of turn the recording off and see if anyone wants to explore matters further. So anyone else? Okay, Linda, are you happy to hang around a bit longer?
Yeah, sure.
Yep. So I don't think I can turn the recording off, can I? So if the people could do so.